of these antimicrobial agents, right? The suffixes tell us how much damage they do. So cidal agents are going to kill microbes. And again, you may be bactericidal, which means what do you kill? Yep. Maybe you're going to kill, maybe you'll be virucidal, which is kind of weird because they're not really alive, but you know what I mean. That means they're going to destroy viruses. And sometimes you may even see the term germicide. We haven't talked about a germ. Germ is this weird word that I try not to use too much because it basically means a microbe that can cause disease. But it's kind of non-specific, right? Could be a virus, could be a fungus, could be a bacteria, we don't know. Bactericidal. The bacterial, and then you add cidal. Oh, the V, virucidal. Like a virus, yeah. Great question. Sorry, V's and B's. Okay. We contrast that, right? So these are going to kill. We're going to contrast that with agents that are blank static. These are going to inhibit or stop growth of microbes. Okay. So again, you may have something that is bacteriostatic. You may have something that is fungistatic. If you use a compound, let's say you use a disinfectant that is bactericidal, after you use it and you walk away, are those bacteria going to come back? Well, they could like rain down. But generally speaking, the ones that you killed are dead, right? On the other hand, what about if you use something that is bacteriostatic? After you remove the bacteriostatic agent, now those bacteria could start to grow again. So it just kind of, but we're going to see that in some cases, especially when we get to chapter 9 and we're talking about what happens inside a patient, because inside a patient, you have two different things that are working together. We're going to be having our antimicrobial chemotherapeutic, but what else do you have in you all the time, hopefully, that is going to help to fight off pathogens? Your immune system, right? So in some cases, especially when we're talking about in a patient, a static agent is holding back the pathogen's growth until that immune system can kind of step in and then finish the job. So we'll talk about that. When we talk about Unit 3, our third exam is when we're going to talk about the immune system. Yay? It's my least favorite. But we got to do it. This is where are my people who are in A and P, B? Like your worlds are going to kind of merge because Dr. Morissette also talks about the immune system. He talks about it from a very system level, organs. Is that my thing? I'm going from molecules up and we're going to kind of meet in the middle of the cells. All right. Oh boy. Let's take a look. All right, put a big star here. This is a big chart that talks about all the different types of microbial control methods. Again, and we are here, this one includes, right, what is down here in yellow? Chemotherapy, so that is going to be chapter 9. Just as a reminder. Okay. So you can see we break this into 4 big categories. What are the 4 big categories? Physical agents, so things that are going to impact temperature, radiation, levels of water. There are also chemical agents. And then we will talk about, actually this one you're going to do on your own. So there's some videos about mechanical removal methods. Basically, this is what we're talking about when we talk about using a filter. How many of you filter your water? right? So this is one of the things, right? You're trying to filter out, you could potentially be filtering out microbes. You could also be filtering out, chemicals, depending on the size of the filters. And then we'll briefly talk about biological agents that can be used to help control the growth of microbes as well. Okay. Within these different methods, you're going to see, right, that some of the things we're going to talk about are sterilizers. Okay. What does that mean again? Right, which makes sense. What is incineration? Fire, right? Would I ever incinerate a patient? No. This is intrinsically like, oh yes, how this is start, right? So you can't do that. I also can't put you in an oven. It's a bad idea. So, some of these are disinfecting, which means we're going to be reducing the levels of pathogenic organisms, right? But not necessarily getting rid of everything. Some of these are antiseptic, meaning that we would use them on living tissue. And chemotherapeutics are the ones that we use inside living tissue. Okay. Yes, Elizabeth.
So the application of these things, is it more often that you have to use like some of them multiple steps in order to do? Like, because I know you can like filter water, but you can also put UV light on it.
Right. Yeah. So sometimes it depends. I guess that's a great question. It depends. We're going to go through some examples. So one of the things that I will do, I promise you that one of the questions on the next exam will be, you need to get rid of the microbes from object X. Choose whether you think it needs to be sterilized, disinfected, antiseptic, or sanitized, and tell me which method you would use and why. In some cases, yes, you might want to combine them. It kind of depends, right? If you really need it to be sterile, then you might use multiple methods compared to if you're like, I just need to like knock them back and sanitize. And some of that depends on what you're doing, what you're treating, and some of it depends on the circumstances around why. We'll get some examples of that. Marissa. Because we typically, because it reduces, it doesn't get rid of as much. So yeah, it's kind of like a higher level. That's a great question. So honestly, the chemical methods and the heat, some of those are sanitizing if you use either less time or less extreme. We'll go over some examples. Okay. Sound good? All right. So, before we do that, let's talk a little bit about, so we just talked about microbial growth, right? Remember this? What's that? A growth curve, right? So we're going to see that the same thing can happen when we kill microbes. We don't kill the microbes all at once. We reduce the population over time, and that's part of why we have to think about how long we expose microbes to things. We're going to talk about how you calculate the decimal reduction time. What's the root of the word decimal? 10. So we're going to be talking about leaving 10% after each decimal reduction time. We're killing 90, we leave 10. Kill 90 again, we leave 10. See how that works. And then we'll talk about how some, right? So again, when we look at these, right, like the agent effectiveness is often tied to what it actually does. Sterilizing agents tend to be the most effective because they get rid of absolutely everything. Antiseptic agents tend to be less effective because they're safe for use on a patient. Okay. So let's just talk again, the pattern of microbial death, right? So when we look at how we're going to reduce time, right, we're going to see that microbes don't die instantaneously. They didn't grow instantaneously and they don't die instantaneously. But it does follow a pattern where we often see that same log scale again because we're going to see what's called exponential death. Before we talked about exponential growth, now we're going to be talking about exponential death. All right, and again, just as a reminder, remember what did VBNC stand for? Viable, but not culturable. And we always want to be asking ourselves, when we're talking about effectiveness, how do we measure whether we've killed the microbes or not? Often we're stuck asking, do they grow? Right? Because they're tiny and I can't take their pulse. And I can't look for whether they're breathing. I can do a couple things. I can try and see if they're making ATP. Sometimes I can measure their oxidation reduction chemistry. There's a couple things I can try to do. But again, these viable but not culturable organisms can be problematic for trying to figure out whether you've killed things or not, because they're kind of hanging out in the interim. Okay. Okay, so here is typically what we're looking at, right? So we said often when we're killing microbes, we see this exponential decline, right? So remember, on this log-based scale, 6 really means 10 to the 6th microbes, right? So we're going from 1 million, what's that, to 10 to the 5th, to 10 to the 4th, right? So here what we're seeing is that our decimal reduction time, so the D is equal to the time to kill 90% of the microbes. So if we have 10 to the 5th, so if we're killing 90%, how much is left? Leaving 10%. What is 10% of 10 to the 5th? 10 to the 4. So we're looking at, so each one of these log reductions, so going from 4 to 3 is a 90% reduction. We're leaving 10 behind. So that's what, so if we want to know what the decimal reduction time is, maybe we want to know how much time does it take to go from 10 to the 3rd, which we start at 3 minutes, and we go to 10 to the 2, which happens at 4 minutes. So how long did it take us to reduce from 10 to the 3 to 10 to the 2? 1 minute. So in this case, the decimal reduction time is 1 minute. Does that make sense? Yes, Grace. D equals the time to kill 90% of the microbes, leaving 10% still alive. But it's iterative, right? So if you start off, then you take 90% of that 10%, right? And you get down to 1. You just keep going. Okay. So you can kind of see this here, right? So if with a 1 minute decimal reduction time, every minute we drop. We go from 10 to the 6th to 10 to the 5th, 10 to the 4th, right? And because we're killing 90% of the total, and that leaves 10%. Does that make sense? That's another way of looking at the data in that graph. All right, I don't want to talk about the z-value. It's hard enough for you guys to handle the d-value. All right, this may show up in the homework. Can't remember, I don't think so. But if it does, you have the information. All right. Let's take a break and do a check. All right, so if you're working in a clinical setting, you're a medical professional, what are some of the things what's the strategy you should think about when selecting a method of microbial control?